In late 2025, as 3I Atlas, the interstellar comet with a coma half the size of the Sun, swept deeper into our solar system, NASA prepared an experiment unlike any before. A mission was greenlit to probe and, if possible, deflect a fragmenting body whose behavior had baffled astronomers for months. But when the attempt finally came, something unexpected happened. Tonight we explore what NASA struck, what went wrong, and what that means for our understanding of interstellar visitors. Before we go any further, take a moment to tell us which country you're watching from and what the exact time is right now. And don't forget to subscribe if you want to know more about 3I Atlas. When the first whispers of an impact mission against 3I Atlas surfaced inside NASA's Planetary Defense Coordination Office, most assumed it was nothing more than contingency planning. The comet, after all, posed no direct threat to Earth. Its trajectory was hyperbolic, meaning it would pass through the solar system once and never return. Yet the sheer strangeness of this interstellar visitor forced a rethink. For months, telescopes had been reporting activity from the comet at distances where sunlight should have been too weak to trigger outgassing. Carbon dioxide jets were already erupting from its surface beyond the orbit of Jupiter. Its coma, an enormous halo of gas and dust, expanded until it reached nearly half the size of the Sunday. It was not behaving like any comet scientists had ever studied. The unusual activity created a deeper concern: fragments. As comets heat up, pieces often break away from the nucleus. Most are small, harmless chunks of ice and dust. But in rare cases, massive fragments can survive, creating unpredictable hazards. Models suggested that if even a modest fragment separated and shifted trajectory under non-gravitational acceleration, it could potentially wander into the orbital neighborhood of Earth or Mars within a few years. The odds were still tiny, but when multiplied by the unknowns of an interstellar object, NASA decided that tiny was not acceptable. The decision was not driven by fear alone. It was also an opportunity. Since the double asteroid redirection test in 2022, NASA had proven it could strike a celestial object with precision and measure the effects. But DART had targeted a small, predictable asteroid orbiting another asteroid. 3I Atlas was an entirely different beast. Fast, volatile, and chemically exotic, it offered a one-time chance to test how kinetic impactors perform against objects from beyond our solar system. Some argued it was irresponsible to interfere with such a unique scientific treasure. Others countered that the only way to truly learn how alien comets respond to force was to try. By mid-2025, the internal debate had hardened into two camps. Planetary scientists pleaded to preserve the comet untouched, calling it the Rosetta Stone of interstellar chemistry. Planetary defense specialists argued for action, warning that ignoring the risk, however small, left humanity vulnerable. The final decision came down to a compromise. NASA would not attempt to alter the comet's main trajectory. Instead, it would send a small, fast impactor to strike a dense clump of ejected material in the coma, a region where observations showed repeated condensation of dust and gas. By targeting this cloud, the mission could measure how interstellar particles responded to direct force, while avoiding any attempt to change the path of the comet's core. The plan had another appeal. Because the coma was so diffuse, any impact would act as a natural laboratory. High-velocity collisions between spacecraft and alien dust would release plumes of vapor that instruments could analyze remotely. NASA engineers viewed it as a chance to sample chemistry without the cost of a full sample return mission. Even if the strike failed in traditional terms, the data alone would be priceless. Still, questions remained. What if the impact destabilized the nucleus, accelerating fragmentation? What if it triggered unpredictable plasma interactions with the solar wind? And perhaps most uncomfortably, what if the strike revealed behaviors that suggested technology rather than nature was at work? These were extreme hypotheticals, but they hovered in the background. In August 2025, the administrator signed off. The mission would be greenlit under a rapid response authorization, similar to programs designed for asteroid emergencies. The spacecraft, adapted from existing hardware, would ride a Falcon Heavy into a transfer orbit by early October, aiming to intercept the comet weeks before perihelion. The cost was modest by NASA standards, but the symbolic weight was immense. For the first time in history, humanity would strike an object that came from another star system. The decision marked a turning point. It was no longer enough to simply observe interstellar visitors passively through telescopes. The age of active engagement had begun, But as history would soon show, even the best planned missions can produce outcomes that surprise the very people who conceived them. Once the decision was made, attention shifted to the design of the mission itself. The challenge was unlike any NASA had faced before. They were not preparing to rendezvous with a familiar asteroid in near-Earth space, nor to orbit a relatively stable comet from the outer solar system. They were attempting to reach and strike an interstellar visitor, traveling at more than 90,000 kilometers per hour, shedding gas and dust in unpredictable jets, and surrounded by a coma so large that the word atmosphere seemed more appropriate than halo. The first question was scale. A full-scale spacecraft with heavy instruments would take years to design and launch, and 3I Atlas would not wait. Its hyperbolic path meant that by 2026 it would already be heading back into the deep interstellar dark, beyond the reach of practical spacecraft. A rapid solution was needed. The answer came in the form of heritage technology, drawing directly from the double asteroid redirection test launched in 2021. That mission had used a small, relatively simple kinetic impactor to strike Dimorphos, a moonlet of the asteroid Didymos, proving that a spacecraft could change an asteroid's trajectory by sheer momentum transfer. For 3I Atlas, the approach would be similar but scaled to new extremes. Instead of targeting the nucleus, engineers selected a compact impactor designed to penetrate a dense knot of dust and ice within the coma. The spacecraft would be lightweight, with most of its mass devoted to shielding and navigation systems. Precision mattered more than force. Because of the immense velocity difference, even a small craft weighing just a few hundred kilograms would release the energy equivalent of several tons of TNT on contact. The point was not to destroy anything, but to provoke a reaction measurable by telescopes and sensors across the solar system. Guidance was the second major hurdle. Comets are notoriously difficult to track, and interstellar comets more so. Their jets create non-gravitational forces that shift their trajectories day by day. To hit such a moving target required advanced optical navigation systems capable of locking onto brightness variations in the coma itself. Engineers developed algorithms that could adjust in real time, correcting the impactor's path without waiting for delayed instructions from Earth. In many ways, the spacecraft would fly itself in the final hours of approach, relying on a kind of artificial instinct rather than human commands. Communications also posed a problem. Dust and plasma around 3I Atlas were expected to interfere with radio signals. To mitigate this, the mission was designed with redundancy. Multiple antennae, high gain and low gain, were included to ensure at least some telemetry would return, even if conditions became chaotic. Yet the team accepted that the spacecraft might go silent at the moment of impact. In that case, ground-based observatories and orbiting satellites would provide the crucial data. Watching the comet for any sudden brightening, shifts in tail geometry, or electromagnetic disturbances. The science payload was deliberately simple. A compact spectrometer would record chemical signatures in the coma as the spacecraft approached. A dust analyzer would measure particle size and density. Small imagers would capture close-up views of the target material in the final seconds before collision. These instruments were not expected to survive the strike, but even a few moments of data would offer priceless insights into the chemistry of alien ices. The mission timeline was short and unforgiving. A Falcon Heavy launch window opened in early October 2025, carrying the impactor on a high-energy trajectory toward the comet. Intercept was planned for late October, just days before 3I Atlas reached perihelion. That timing was intentional. Near perihelion, the comet's activity would be at its peak, making any reaction from the strike far more visible to telescopes on Earth and in space. The design carried risks. Some worried that striking a volatile clump within the coma might destabilize the nucleus. Others feared the dust cloud would be too diffuse to register any meaningful reaction. But engineers argued that the experiment would be informative no matter the outcome. If the impact dispersed material, it would reveal the density of the coma. If nothing happened, it would prove that even interstellar ices resist disruption at certain scales. If the response was unpredictable, that too would expand knowledge. In the end, the mission design reflected a balance of urgency and humility. It was not the largest spacecraft NASA had ever built, nor the most ambitious, but it was the fastest developed, the most daring in its simplicity, and the most symbolic. For the first time, humanity was reaching out not to defend against a threat or to land on a familiar neighbor, but to touch the unknown itself. The impactor was more than hardware. It was a gesture, a small but deliberate act of engagement with the wider galaxy. Whether the mission succeeded or failed, it would mark the beginning of a new era in planetary defense and interstellar science. From the moment astronomers first identified 3I Atlas in July 2025, it was clear that this object did not behave like anything seen before. At first glance, it resembled a comet, a nucleus likely just a few kilometers across, shedding gas and dust as it traveled toward the Sunday. But even in the earliest weeks of observation, anomalies began to appear. By the time NASA considered an impact mission, the differences were undeniable. The most striking feature was its activity at extraordinary distances. Typical comets remain inert until they approach within 2 or 3 astronomical units of the Sun, the region where water ice begins to sublimate. Yet 3I Atlas was already shedding large amounts of gas when it was still beyond 4 astronomical units, farther than the orbit of Jupiter. The explanation lay in chemistry. Spectroscopy revealed that its composition was rich in carbon dioxide and other volatile ices that sublimate at much lower temperatures than water. These ices, rare in comets of our own solar system, suggested formation in an environment far colder than the outer Kuiper belt. They pointed to a birthplace in a distant interstellar nursery, perhaps around a star long gone from our skies. The coma that formed was unlike any astronomers had recorded. By September 2025, it had expanded to nearly 700,000 kilometers across half the diameter of the Sun itself. The nucleus was a tiny speck hidden deep inside, yet the envelope of gas and dust was vast enough to engulf multiple planets. Unlike most comets, which produce comas roughly spherical in shape, 3I Atlas displayed forward, brightening an asymmetry in which its brightest features appeared ahead of its orbital path rather than behind. This suggested violent, uneven outgassing and perhaps rapid rotation, creating plumes that curved into unusual patterns. Its tail added another layer of mystery. Instead of a single dust tail and a thin ion tail, 3I Atlas displayed multiple, shifting streamers that changed shape from week to week. Some resembled sheets or curtains of plasma rather than the thin rays expected of a comet. These structures appeared to respond directly to fluctuations in the solar wind, almost as if the object were interacting with the Sun's magnetic field on a larger scale than comets usually manage. To planetary defense experts, this was more than a curiosity. It meant that predicting the motion of 3I Atlas was far more difficult than with ordinary bodies. Non-gravitational acceleration, the subtle push from asymmetric jets, was greater than expected, forcing orbital models to be updated every few days. Another reason 3I Atlas stood apart was its sheer speed. Traveling on a hyperbolic trajectory, it moved faster than any bound object in the solar system, nearly double the velocity of typical comets. That speed was both a challenge and an opportunity. For mission planners, it meant that an impactor would have to strike at precisely the right moment, with no possibility of second chances. For scientists, it offered a chance to study interstellar matter passing through our solar system at galactic velocity, providing a glimpse of chemistry and physics forged far beyond the Sun's reach. Even the question of its internal structure remained unsettled. Some models suggested a porous, fragile nucleus similar to solar system comets. Others hinted at a denser, more resilient core, shaped by billions of years of exposure to interstellar radiation. The truth could only be guessed at from afar. Striking even a small clump of material in its coma might provide clues about density, cohesion, and the behavior of these alien ices under stress. But perhaps the greatest difference was symbolic. This was not just another visitor from the Oort cloud, not a frozen relic from our own solar system's birth. This was the third confirmed interstellar object ever detected, following Oumuamua in 2017 and Borisov in 2019. Oumuamua had left scientists arguing whether it was a comet, an asteroid, or something stranger. Borisov had behaved like a typical comet, offering reassurance that interstellar visitors could look familiar. 3I Atlas, however, broke the pattern. It was active at vast distances, chemically exotic, and physically enormous in its effects. It straddled the line between familiar and alien, forcing astronomers to reconsider what they thought they knew. This was why NASA felt compelled to act. 3. I-Atlas was not just different. It was a once-in-a-civilization chance to learn how matter from another star system behaves when it plunges through ours. Its differences were not minor quirks, but fundamental departures from known cometary physics. To ignore such an opportunity would mean losing insights that might not return for centuries. At the same time, those very differences made it unpredictable, volatile, and potentially unstable. It was this tension between opportunity and risk that defined every decision about how humanity would respond to the arrival of 3I Atlas. Predicting the path of a comet is never simple. Even the most familiar members of our solar system, observed for centuries and modelled with exquisite precision, still surprise us with small deviations in their orbits. These shifts come from outgassing the process by which solar heating releases jets of gas and dust that act like miniature thrusters. With 3I Atlas, however, these challenges were magnified to a degree that pushed the limits of celestial mechanics. At first, astronomers tried to apply the same methods they used for ordinary comets. Telescopic observations were combined with radar measurements and fed into orbital models. The trajectory was clearly hyperbolic, confirming that 3I Atlas was not bound to the Sun and would eventually leave our system forever. But beyond this broad outline, the details quickly became unstable. Every few days, the predictions shifted. The comet refused to behave like the objects the equations had been built to describe. The main problem was the intensity of its activity. For a nucleus only a few kilometers wide, 3I Atlas was shedding vast amounts of material. This did not happen uniformly across its surface. Instead, jets erupted from discrete vents, sending out streams of gas at hundreds of meters per second. Each jet created a tiny thrust, imperceptible on its own but significant when sustained over days and weeks. For most comets, such effects can be modelled with relative accuracy. For 3I Atlas, the forces were so large and so irregular that the models broke down. By September 2025, the uncertainty in its predicted position had grown into tens of thousands of kilometers. For NASA's planned impactor mission, this was unacceptable. A spacecraft traveling at interplanetary velocities cannot afford to miss by even a fraction of a second in timing. Engineers needed models accurate to within just a few kilometers, yet the comet's unpredictable behavior made that goal elusive. Another complication came from the shape of the coma itself. Instead of a symmetrical envelope, 3I Atlas displayed brightening ahead of its orbital path. This suggested that some jets were not only pushing outward, but also acting in directions that altered the comet's momentum in unusual ways. Traditional models assumed that outgassing was roughly radial, pointing away from the Sunday. With 3I Atlas, this assumption collapsed. Non-radial forces, possibly tied to rapid rotation or patchy surface chemistry, bent the trajectory in directions no one expected. The solar wind added further complexity. Plasma from the Sun interacted with the comet's enormous coma, creating drag-like effects that changed depending on solar activity. During geomagnetic storms, sudden bursts of energy could alter the behavior of the coma, increasing the density of ionized particles and shifting the comet's effective cross-section against the solar wind. These influences were small compared to gravity, but over millions of kilometers, they accumulated into measurable deviations. To cope with these uncertainties, NASA and international partners resorted to constant recalibration. Observatories across the world tracked the comet nightly, feeding updates into global databases. Supercomputers ran thousands of simulations, each incorporating slightly different assumptions about jet strength, rotation, and solar wind interactions. The result was not a single prediction but a cloud of possible trajectories, a probability map that shifted day by day. For planetary defense specialists, the situation was sobering. Although the comet posed no immediate threat to Earth, the fact that an object could behave so unpredictably raised questions about how humanity might one day handle a genuine hazard. If this had been an Earth-crossing body, the uncertainty would have been terrifying. How do you plan a deflection when the object itself resists being modelled? The strain was not just technical but philosophical. Astronomers pride themselves on precision. The orbits of planets and asteroids can be predicted centuries in advance, a triumph of Newtonian mechanics refined by modern computing. 3I Atlas undermined that sense of certainty. Here was an object that laughed at equations, reminding scientists that the universe is full of bodies forged under conditions far beyond those of our solar system. Its chemistry, structure, and outgassing dynamics carried the fingerprints of a different star, a different history, and perhaps different rules of behavior. For the mission team, the challenge became one of adaptability. Rather than relying on long-term predictions, they designed the spacecraft's navigation to be reactive, correcting its course in real time based on what it saw. In effect, the engineers admitted that no Earth-based model could keep up with 3I Atlas. Only a spacecraft flying into its environment could close the gap between prediction and reality. Trajectory calculations, once considered routine, had become a frontier of exploration. Each error, each unexpected deviation, was not a failure but a clue. 3. I-Atlas was teaching astronomers that interstellar comets cannot be forced into the molds built for local ones. Their paths are not just shaped by gravity, but by alien chemistry, volatile physics, and interactions with the sun that defy easy categorization. The strain on the models was also their reward, pushing human understanding into territory no equation had yet mapped. The mission to strike 3I Atlas began not with silence but with thunder. On an early October morning in 2025, a Falcon Heavy roared to life at Cape Canaveral, lifting the small impactor on its way toward an interstellar target unlike any humanity had ever attempted to touch. The launch itself was almost routine by modern standards. SpaceX had perfected the art of heavy-lift rockets, and 3 boosters powered the craft into the sky. Yet everyone watching understood that this was no ordinary mission. For the first time in history, a human-made object was being sent to collide with a body that had traveled across the galaxy. The payload was modest in size but ambitious in purpose. At its heart was the kinetic impactor, a compact spacecraft designed for precision rather than endurance. It carried small navigation cameras, a lightweight spectrometer, and dust analyzers to gather data on approach. Its final task was simple: to collide with a dense clump of particles within the comet's vast coma at extraordinary speed. The spacecraft's simplicity was deliberate. Engineers had stripped away anything unnecessary, understanding that survival after impact was impossible. Every gram had to serve guidance, sensing, or momentum. The journey began with a carefully timed injection burn, placing the spacecraft on a direct trajectory toward 3I Atlas. Because the comet was moving at such high velocity, the window for interception was narrow. The trajectory had to be calculated with relentless precision, accounting not just for the comet's gravity and outgassing, but also for the constant changes in its position. Navigation teams at NASA's Jet Propulsion Laboratory worked around the clock, updating models based on fresh telescope data every night. Small course corrections were planned into the mission from the start. In fact, the spacecraft was designed to fire its thrusters repeatedly, fine-tuning its path as new observations came in. For weeks, the spacecraft cruised through interplanetary space, guided by autonomous software. Signals sent from Earth took several minutes to arrive, too long for human operators to micromanage the approach. Instead, the navigation system relied on optical cameras that locked onto the faint glow of 3I Atlas and adjusted the spacecraft's course accordingly. Each correction was subtle, often only a few centimeters per second in velocity, but together they made the difference between a clean strike and a miss by thousands of kilometers. By mid-October, the comet was already brightening as it neared perihelion. Its coma expanded and tails shifted shape under the influence of the solar wind. From Earth, it appeared as a faint greenish blur in sensitive telescopes, but for the spacecraft it was becoming a looming presence. At first, the cameras captured nothing more than a star-like dot against the black. Then, frame by frame, the object grew into a diffuse cloud that filled the field of view. To mission control, it was a surreal moment. Humanity's first close look at an interstellar visitor, seen not from the safety of distant observatories, but from the vantage point of an approaching probe. As the spacecraft drew closer, conditions became less predictable. Dust levels increased, and sensors recorded flashes of charged particles colliding with the hull. Engineers had worried about this phase. Since too much dust could disable instruments or even destabilize navigation, but the small impactor was resilient. It kept adjusting its flight path, threading through a storm of alien particles that no spacecraft had ever encountered. The final hours before impact were tense. Ground teams monitored telemetry as the probe's onboard software took over completely. Humans could no longer intervene. The time delay between Earth and the spacecraft was too great. The probe was on its own, flying into the unknown with nothing but algorithms and cameras to guide it. Data streamed back in bursts, images of the coma, measurements of dust density, faint chemical signatures from the spectrometer. Each byte of information was precious. A direct sample of matter formed in another star system billions of years ago. Finally came the moment of arrival. The spacecraft, closing in at over 25 kilometers per second, locked onto its designated target, a dense knot of gas and ice within the coma, glowing faintly brighter than its surroundings. The navigation cameras tracked the clump as it grew from a blur to a shape. Mission Control held its breath. There would be no explosion visible from Earth, no fireball in the sky. The impact would occur silently, deep in space, and only its aftermath would tell the story. Then the signal from the probe went silent. On Earth, screens froze. Mission Control knew this was expected. At the moment of collision, the spacecraft's instruments would be destroyed. What mattered now was whether telescopes around the world and satellites in orbit would see the results. Had humanity truly struck the alien visitor, or had the final hours of calculations failed in the face of an unpredictable interstellar body? The launch and journey were complete. The strike had been attempted. Now the universe itself would reveal whether NASA's gamble had succeeded. The world never saw it happen directly. There was no great flash across the night sky, no fiery display visible to the naked eye. The strike against 3I Atlas occurred in silence, a collision between a small spacecraft and a diffuse cloud of alien matter more than 100 million kilometers away. Yet the moment was as dramatic as any event in the history of space exploration. For the first time, humanity had deliberately touched an object from another star system. As the spacecraft closed in during its final minutes, it was flying blind to human eyes. The time delay between Earth and the probe meant that no one at Mission Control could guide it in real time. The last commands had been uploaded hours earlier. From then on, the navigation algorithms and the optical cameras aboard the craft made every decision. Telemetry showed the systems performing flawlessly. The onboard computer locked onto a brightening clump within the coma, a region of higher dust density that had been chosen as the strike target. To the spacecraft, the knot of material appeared first as a blur. Then, as seconds passed, it grew rapidly larger in the field of view. Every fraction of a second, the computer adjusted course, firing tiny thrusters to keep the target centered. At a closing speed of more than 25 kilometers per second, there was no room for error. Even the smallest misalignment would have meant sailing through empty coma with nothing to show for the mission. Back on Earth, Mission Control followed the stream of data in tense silence. The cameras transmitted rapid snapshots, each one showing the clump swelling against the background stars. Dust detectors recorded rising impacts, each grain of alien material striking the hull at thousands of kilometers per hour. The spectrometer captured its last chemical traces: carbon dioxide, methane, traces of exotic molecules not yet fully catalogued. Then, with only seconds left, the stream became erratic. Signals wavered, and then, in an instant, went dark. Impact. There was no confirmation from the spacecraft itself. The strike had vaporized it instantly, scattering fragments into the surrounding cloud. All that remained was the response of the comet. For a few minutes, Earth's telescopes saw only the same faint green glow, unchanged and unmoved. Some began to wonder if the collision had been too small, the clump too diffuse, the effort wasted. But then the data started to arrive. The first clue came from the Hubble Space Telescope. Within 20 minutes of the strike, Hubble recorded a sudden brightening near the comet's nucleus, a flare that grew and spread outward. Ground-based observatories confirmed it. The coma was expanding more rapidly than before, lit by sunlight scattering off newly liberated dust. The impact had done its work. It had shaken loose material that had been trapped within the alien ices, creating a new wave of outgassing visible across millions of kilometers. But the reaction was not what scientists had expected. Instead of dispersing smoothly, the new jets formed narrow, focused streams, almost like nozzles venting high-pressure gas. These streams bent under the influence of the solar wind, creating twisted ribbons that stretched across space. Plasma instruments aboard Earth-orbiting satellites picked up disturbances in the interplanetary magnetic field, subtle ripples that coincided with the timing of the impact. Somehow, the release of gas from 3I Atlas had interacted with the solar environment in ways far more dramatic than anticipated. At Mission Control, cheers broke out at the confirmation of success. But they quickly gave way to puzzled silence as the scope of the changes became clear. What had been intended as a simple test of cometary material had triggered a chain of events that no model had predicted. The comet was more volatile, more reactive, and more electrically connected to its environment than anyone had guessed. The strike had worked. It had produced data volumes of it, but it had also opened a door onto mysteries that scientists were only beginning to grasp. The moment of impact was supposed to mark the end of the mission. In reality, it was the beginning of the most unexpected chapter of all. For now, the small spacecraft was gone, sacrificed in the name of exploration. But in its destruction, it had delivered something far greater, the first true contact with an interstellar wanderer, and the first undeniable sign that these objects are not just silent stones drifting through space. They are active, volatile, and full of surprises. The strike moment had passed, but its consequences were only just starting to unfold. In the hours following the impact, scientists across the world began piecing together what had happened. For many, the first measure of success was simply confirmation that the spacecraft had found its target. The silence from the probe after collision was expected, but the flare in brightness recorded by telescopes was undeniable. Humanity had struck an object from another star, and the universe had responded. The first observations came from Earth's largest observatories. Within 30 minutes of the planned impact, the Hubble Space Telescope detected an increase in the coma's luminosity. This brightening was consistent with fresh material being ejected into space, dust and gas, liberated by the violent contact of the impactor with the comet's volatile cloud. From Chile, the European Southern Observatory confirmed the flare, measuring a significant rise in carbon dioxide and carbon monoxide signatures in the comet's spectrum. Instruments in Hawaii added evidence of micron-sized dust particles spreading outward at surprising speed. Each detection was a small but vital confirmation. The mission had worked. On Earth, NASA's Jet Propulsion Laboratory released cautious statements. Engineers and scientists explained that while the spacecraft itself had been lost, the data was already flowing in from telescopes. Success, they reminded the public, did not depend on the probe surviving. It depended on what could be learned from the comet's reaction. By that measure, the first signs were promising. The initial triumph was not only scientific but symbolic. For the first time, humanity had not only observed but also influenced an interstellar visitor. In earlier decades, objects like Oumuamua and Borisov had passed through our solar system untouched, mysteries glimpsed briefly, and then gone forever. 3. Atlas was different. Here, a spacecraft launched from Earth had touched its material, changing its behavior, however slightly. This symbolic leap was not lost on the global audience watching the story unfold. Commentators described it as the moment humanity's reach extended beyond the solar system, a kind of handshake with the wider galaxy. Still, the science was what mattered most. Early models suggested the spacecraft had struck a region of unusually dense dust within the coma. The kinetic energy released was equivalent to several tons of TNT, enough to compress, heat, and vaporize material instantly. This sudden release triggered localized outgassing, producing jets of carbon dioxide and methane that telescopes could measure. Astronomers calculated that thousands of tons of dust had been liberated, enough to increase the comet's brightness by a measurable factor. Perhaps the most reassuring aspect of the first results was that the nucleus itself remained intact. Initial fears that the strike might destabilize the core or trigger fragmentation were unfounded. Observations showed no sign of major structural collapse. The flare came from the outer layers of the coma, not from the nucleus itself. This meant the experiment had succeeded in producing measurable effects without creating a catastrophic disruption. For planetary defense experts, this was encouraging news. It suggested that kinetic impactors could interact with volatile targets without necessarily risking total disintegration. The early hours also brought an unexpected benefit: clarity. For weeks, the comet's trajectory had been difficult to model because of the irregular outgassing. After the impact, new jets provided fresh markers for astronomers to track, allowing them to refine orbital predictions. Ironically, the strike that was meant as a test of physics also improved humanity's ability to forecast the comet's path through the solar system. In mission control, emotions shifted from tension to relief. engineers celebrated the fact that the spacecraft's navigation had performed flawlessly. Striking a target smaller than a city block after a journey of millions of kilometers, to guide a probe across such distances and achieve direct contact, was itself an extraordinary accomplishment. Even if the science had yielded nothing more, the precision of the impact alone was proof of human ingenuity. The initial success of the mission was thus twofold. First, it provided direct evidence that interstellar material could be sampled, however briefly, through impact. Second, it demonstrated that Earth's spacefaring capabilities were advanced enough to engage with objects that entered from beyond the solar system. This dual achievement, scientific and technological, was celebrated not only by NASA, but also by the broader scientific community. Of course, no one knew then that the aftermath of the strike would grow stranger with each passing day. For the moment, success was measured in brightness curves, spectral lines, and the quiet satisfaction of knowing that a spacecraft had done exactly what it was designed to do. Humanity had reached across the void, made contact, and survived the attempt with new knowledge in hand. The deeper mysteries of 3I Atlas would come later. For now, there was cause to celebrate. When scientists first reviewed the data following the impact, they expected a temporary brightening, followed by a gradual return to normal activity. Comets often flare after collisions or natural outbursts, but the effect typically fades within days. With 3I Atlas, however, something far more dramatic occurred. Instead of dispersing quietly, the impact appeared to unlock a deep reservoir of volatile material. What began as a small flare grew into an event that changed the entire character of the comet. The first signs came from spectrographs tracking chemical composition. Within hours of the strike, measurements showed an abrupt surge of carbon dioxide and methane emissions, far beyond what models had predicted. This suggested that the impact had exposed subsurface pockets of volatile ice, which were now venting into space at extraordinary rates. What puzzled researchers was the intensity of the release. The spacecraft had been designed to strike a relatively diffuse clump of dust, not the nucleus itself. Yet the chemical surge looked as if something deeper had been disturbed. Dust measurements told the same story. Telescopes recorded a sharp increase in fine particles spreading outward at velocities exceeding 700 meters per second. For comparison, typical cometary dust flows at a fraction of that speed. The only way to explain such acceleration was a buildup of internal pressure suddenly venting through newly created pathways. It was as though the strike had punctured a valve on a system that had been waiting for release. The visual changes were equally striking. In the days after impact, 3I Atlas's coma expanded rapidly, growing by hundreds of thousands of kilometers. Its brightness rose well beyond forecasts, briefly rivaling the glow of much larger comets. But unlike ordinary dust clouds, which spread evenly, the material formed narrow streams. These jets were so tightly collimated that some astronomers compared them to fire hoses in space. Their geometry suggested that gases were escaping through specific vents, channeling material outward with precision, rather than in random bursts. Perhaps most surprising of all were the electromagnetic effects. Satellites monitoring the solar wind reported disturbances coinciding with the timing of the flare. Instruments on the Solar and Heliospheric Observatory detected ripples in the interplanetary magnetic field that radiated outward from the region. Around 3I Atlas. While comets are known to interact with the solar wind, the magnitude of this event was unusual. It was as though the sudden release of ionized gas had briefly created a shockwave, altering the local plasma environment across millions of kilometers. These effects caught researchers off guard. The mission had been designed with caution, specifically to avoid destabilizing the comet's nucleus. By striking a fragment within the coma, engineers hoped to produce only localized changes. Yet the unexpected release suggested that even a minor disturbance could set off cascading reactions within such an alien object. The physics of interstellar ices, it seemed, played by different rules. Reactions among the scientific community ranged from excitement to unease. On one hand, the event provided an unprecedented opportunity to study volatile chemistry under interstellar conditions. Instruments recorded compounds rarely observed in solar system comets, including exotic hydrocarbons that hinted at unusual formation environments. On the other hand, the scale of the release raised questions about what might happen as the comet drew even closer to the Sunday. If such a small impact could trigger massive outbursts, What would perihelion bring? For planetary defense experts, the episode was both a warning and a revelation. It underscored how unpredictable interstellar visitors could be. In a real threat scenario, attempts to deflect such a body might produce consequences no one could anticipate. Even a controlled strike aimed at a harmless fragment had produced a chain reaction with global consequences for space weather monitoring. It became clear that humanity still had much to learn before confidently handling objects of this kind. For the public, the story took on a different tone. News headlines spoke of NASA waking up, the comet, or poking the dragon. The dramatic increase in brightness made 3I Atlas briefly visible to backyard telescopes, a ghostly reminder that something extraordinary was unfolding far beyond the reach of human eyes. The mission had not only succeeded, it had unleashed a spectacle no one had foreseen. The unexpected energy release changed the narrative entirely. What was meant to be a small experiment had turned into a cosmic event, one that would keep astronomers awake for months to come. The lesson was simple but profound. When dealing with matter forged around other stars, prediction becomes fragile. The universe holds its secrets tightly, and sometimes it takes only a small touch to unlock forces greater than we can imagine. The aftermath of the impact did not stop with the comet itself. While telescopes recorded dust and gas venting into space, satellites positioned throughout the inner solar system began detecting disturbances that rippled far beyond 3I Atlas. What had begun as a controlled experiment quickly escalated into a heliophysical event. The comet, now agitated by the strike, appeared to interact with the solar wind in ways no one had fully anticipated. The solar wind is an invisible stream of charged particles that flows outward from the sun at hundreds of kilometers per second. For billions of years, it has sculpted the space environment of our solar system, shaping magnetospheres, fueling auroras, and carving comet tails into elegant arcs. Normally, when the solar wind collides with a comet's coma, the result is predictable. Ions form a tail pointing directly away from the sun, while dust drifts into a broader, curved plume. But with 3I Atlas, the situation was anything but typical. In the hours following the impact, the solar wind around the comet became turbulent. Instruments aboard the solar orbiter detected sudden fluctuations in particle density and velocity. At first, scientists thought these were routine variations caused by solar activity, but the timing aligned too closely with the outburst, triggered by the strike. The probe's impact had released a flood of ionized gases into the coma, creating a dense plasma cloud that resisted the solar wind like a boulder in a river. This resistance produced shockwaves regions where the solar wind abruptly slowed and heated as it encountered the comet's expanding envelope. Space physicists compared the effect to the bow shock that forms in front of Earth's magnetosphere, but on a far more dynamic scale. Instead of a steady barrier, 3I Atlas created shifting, pulsating fronts of plasma that spread outward, disturbing magnetic field lines across millions of kilometers. The evidence grew stronger as data poured in from other spacecraft. The Parker Solar Probe, orbiting closer to the Sun, picked up irregularities in the heliospheric current sheet, a vast, spiraling structure of charged particles that threads through the solar system. These irregularities coincided with the comet's position, suggesting that the energy release had altered currents flowing through the inner heliosphere. On Earth, magnetometers registered subtle disturbances, minor enough not to disrupt daily life, but clear enough to confirm that something unusual was happening far upstream. For scientists, the event was both bewildering and thrilling. No comet had ever produced shockwaves of this magnitude. Ordinary cometary interactions with the solar wind are small-scale phenomena, detectable only by spacecraft in close proximity. 3I Atlas, by contrast, seemed to generate effects large enough to influence the heliospheric environment across vast distances. Some researchers speculated that the sheer scale of the coma, already hundreds of thousands of kilometers across, acted as a giant plasma antenna, amplifying its interaction with the solar wind. The implications were significant. If interstellar objects like 3I Atlas could create such disturbances, then their passages through solar systems might carry consequences far beyond visual spectacle. They could shape space weather, alter magnetic environments, and potentially impact planetary atmospheres. While Earth faced no direct danger from this encounter, the lesson was clear. The presence of alien matter in the solar wind was not a passive event. It was active, dynamic, and disruptive. News of the shockwaves quickly spread beyond scientific circles. Media outlets seized on the idea of a comet shaking the sun's wind, painting vivid pictures of invisible storms racing through space. The public, still captivated by the brightness flare, now imagined ripples from the comet echoing across the void. While the descriptions were simplified, they were not entirely wrong. The impact had, in a sense, turned 3I Atlas into a temporary engine of space weather. At NASA and ESA, teams scrambled to coordinate further observations. Ground-based radio telescopes tracked unusual emissions from the comet's coma, hinting at interactions between charged particles and magnetic turbulence. X-ray observatories detected faint signals as solar wind ions collided with neutral atoms, producing high-energy photons. Together, these measurements built a picture of a complex electromagnetic storm centered on an object that had crossed into our solar system from another star. The realization was sobering. Humanity had struck 3I Atlas in the name of science, but the comet had struck back in its own way by revealing how little we understood about interstellar plasma physics. The shockwaves in the solar wind were not destructive to Earth, but they were a reminder that even small interventions could ripple outward in unpredictable ways. The cosmos, it seemed, had its own way of reminding us that no experiment is ever entirely under human control. Every space mission lives and dies by communication. From the moment a spacecraft leaves the launch pad, its radio signal is the only lifeline connecting it to Earth. Engineers spend years designing redundant systems, shielding electronics, and testing antennas to make sure that link never fails. With the 3I Atlas impactor, those precautions were no less rigorous. Yet, in the hours around the strike, something happened that no one had fully anticipated. The signal faltered, and for a time, humanity lost its voice in the darkness. At first, everything seemed normal as the spacecraft closed in on its target. Data streamed back in, bursts images of the brightening coma, dust counts rising steadily, and the faint chemical fingerprints of alien gases. Mission control followed along as though riding on the spacecraft's shoulder. Then, about an hour before impact, the telemetry became irregular. Packets of data arrived incomplete, some garbled, some missing entirely. Engineers suspected interference from dust and plasma, which had been predicted as a possible hazard, but the scale of the disruption was greater than the model suggested. The comet's coma was no simple fog of particles. It was a charged environment filled with ionized gas colliding with the solar wind. These interactions created electromagnetic noise, the kind that could scatter or distort radio signals. The spacecraft carried both high-gain and low-gain antennas, designed to switch automatically if one became compromised. But even with redundancy, the disturbances grew stronger as the probe dived deeper into the cloud. By 30 minutes before impact, Mission Control was receiving only fragments of information. Images arrived as streaked mosaics, chemical data as half-complete lines. Dust detectors pinged wildly, suggesting the spacecraft was enduring a storm of particles, each strike threatening to erode its delicate sensors. Then, just minutes before collision, the signal flickered entirely. Screens froze, the countdown to impact reached 0, and then silence. The room at NASA's Jet Propulsion Laboratory fell quiet. Engineers knew the spacecraft was designed to be destroyed on impact, but the expectation had been to receive data until the final second. Instead, contact had been lost early, leaving a gap in the mission record. No one could say for certain whether the probe had struck its target cleanly or had been disabled by the chaotic environment before it reached the mark. For hours, teams scrambled to re-establish contact. They sent repeated pings across the deep space network, hoping to catch even the faintest echo from the craft. None came. It was gone, swallowed by dust and distance. All that remained was the evidence gathered by telescopes and observatories back on Earth. The glitch was more than an inconvenience. It raised questions about how well humanity could operate in such alien conditions. Earth's spacecraft had navigated through cometary comas before, most famously during ESA's Rosetta mission to Comet 67P, but 3I Atlas was not a local comet. Its chemistry and plasma environment were foreign, and its coma was orders of magnitude larger. The impactor had ventured into a storm unlike anything designed for terrestrial laboratories. In the weeks that followed, engineers reviewed the fragments of data that had made it through before the blackout. Some suggested that the failure was not a malfunction but a natural consequence of flying into an environment so electrically active that radio waves simply could not escape. Others speculated that the dust storm had shredded key components earlier than expected. Whatever the cause, the lesson was clear. Future missions to interstellar comets would need far stronger shielding and new communication strategies, perhaps using laser-based systems less vulnerable to plasma interference. Despite the loss, the mission was not a failure. Ground-based telescopes confirmed the strike through the sudden brightening of the comet, and space-based observatories measured the chemical surge. The missing minutes of telemetry were frustrating but not fatal. Still, for those who had worked on the spacecraft, the silence was painful. Years of design and planning had ended in a flicker of static. A reminder that even in triumph, space exploration carries moments of uncertainty. The communication glitch became a metaphor as much as a technical issue. Humanity had reached out to touch an object from another star, but at the critical moment the connection faltered. It was as if the universe itself had decided to keep part of the story hidden, while the spacecraft itself was silenced forever in the instant of impact. The story of what happened to 3I Atlas continued to unfold through the eyes of Earth and its orbiting instruments. From mountaintop observatories to backyard telescopes, humanity turned its gaze toward the interstellar visitor, eager to read the signs written in light and motion across the sky. The first major confirmation came from the Hubble Space Telescope. Within less than an hour of the expected collision, its sensitive cameras detected a brightening in the comet's coma. At first, the increase was subtle, only a few percent, but by the next orbit, the glow had doubled. This rapid escalation suggested that fresh material had been ejected in large quantities, scattering sunlight and expanding the comet's visible envelope. For mission scientists, it was the proof they needed. The strike had not been in vain. On the ground, telescopes in Chile, Hawaii, and the Canary Islands joined the watch. Using spectrographs, they measured sudden spikes in carbon dioxide and carbon monoxide emission lines, accompanied by weaker signals of methane and ammonia. These molecules told a story of ices being exposed and vaporized, gases venting into space that had likely remained buried for billions of years. To planetary chemists, this was gold, direct evidence of the chemical makeup of a body formed in another star system. Amateur astronomers also played a role. In dark skies far from city lights, skilled observers reported that 3I Atlas appeared slightly brighter in binoculars than it had the night before. Images posted online showed a coma swelling larger than predicted, its edges diffuse and shifting. While professionals relied on spectrographs and high-resolution imaging, amateurs provided real-time monitoring, creating a global network of eyes feeding into the shared narrative of the comet's response. Radio telescopes added another dimension. The Very Large Array in New Mexico detected emissions from ionized gases interacting with the solar wind. These signals, invisible to optical telescopes, revealed the turbulence unfolding in the plasma environment surrounding the comet. At the same time, X-ray observatories recorded faint but distinct bursts of high-energy photons, evidence that solar wind ions were colliding with neutral atoms in the newly ejected cloud. Together, these observations confirmed what many had suspected. The strike had not simply shaken loose dust, it had ignited a cascade of electromagnetic interactions that rippled outward through space. In Europe, the European Southern Observatory tracked changes in the shape of the comet's tail. Before impact, the tail had already been long and complex, twisted by the solar wind. Afterward, it split into multiple streamers, some straight, others curved, suggesting that the fresh outgassing was reshaping the way particles interacted with the sun's magnetic field. To scientists, this was not just a curiosity. It was a chance to see plasma physics play out on scales too large to recreate in any laboratory. For the public, the observations became a shared spectacle. News outlets published side-by-side images of the comet before and after the impact, highlighting the swelling coma and the brighter core. Headlines spoke of NASA punching a hole in an interstellar comet, though scientists were quick to correct the language. Nothing so crude had happened. Instead, a precise experiment had produced results more dramatic than expected. Yet, the effect on public imagination was undeniable. Across social media, people shared photos of the faint green smudge rising in the night sky, each image a reminder of humanity's reach beyond its own world. For the scientific community, The Earth-based observations were more than confirmation, they were calibration. With the spacecraft gone, the only way to measure the impact's consequences was through coordinated tracking from Earth and orbit. Teams worked around the clock to synchronize data, compare light curves, and refine models. The result was a collective effort spanning continents, instruments, and disciplines. No single telescope could tell the whole story, but together they revealed a picture of a comet suddenly transformed. Earth could not hear the spacecraft's final words, but by watching carefully, by studying the light, the chemistry, and the subtle shifts in plasma, humanity continued the conversation in another way. The planet itself became the laboratory, and every photon that reached it carried a message from the alien wanderer. For decades, astronomers have relied on sophisticated models to forecast how comets behave. These models are built on centuries of observation, refined with modern computing, and verified against missions like Rosetta, Deep Impact, and DART. They take into account solar heating, sublimation of ices, rotational dynamics, and the steady push of jets streaming into space. When applied to most comets, the predictions match reality with impressive accuracy. With 3I Atlas, however, the models began to collapse almost immediately. The first cracks appeared in trajectory forecasts. Observers had already noticed that the comet's path shifted unpredictably, as though it were being nudged by invisible hands. Standard non-gravitational acceleration terms, usually enough to describe jet activity, failed to account for the degree of drift. Teams tried adjusting parameters, rotational period, outgassing strength, orientation of jets. Still, the numbers refused to converge. The comet's enormous coma seemed to act as a giant sail, coupling to the solar wind in ways no one had anticipated. After the impact, the problem grew worse. Telescopes confirmed the brightening and the new jets of gas, but their behavior was chaotic. Models predicted that the coma would expand evenly before fading back to baseline. Instead, it split into filaments that bent and twisted in real time. Some streamers brightened suddenly, only to vanish within hours. Others curved against expected solar wind directions, as if guided by forces beyond simple radiation pressure. Spectroscopy added another layer of confusion. Emission lines showed sudden surges of carbon dioxide and methane, but their relative ratios fluctuated wildly from night to night. Standard thermal models assumed steady sublimation governed by solar distance, yet 3I Atlas produced irregular bursts, releasing exotic hydrocarbons at temperatures where they should have remained frozen. To chemists, this implied a layered structure in the nucleus, perhaps containing ices from environments colder than any region of our solar system. To modelers, it was a nightmare. The equations assumed homogeneity. The reality was patchwork and unstable. Computational simulations struggled. Supercomputers ran thousands of variations, tweaking assumptions to fit the data. No single solution explained all observations. One model could match the light curve but failed to reproduce the tail geometry. Another could replicate the plasma disturbances but predicted dust velocities far lower than measured. Even hybrid approaches combining cometary physics with space weather dynamics fell short. 3. Atlas seemed to obey rules that did not fit comfortably within existing frameworks. For many researchers, the failure was humbling. Astronomy is a discipline rooted in predictive power. To guide spacecraft, to plan observations, to compare theory with reality models are the scaffolding that supports all interpretation. With 3I Atlas, the scaffolding shook. The comet was not simply unpredictable, it was actively defying the categories designed to contain it. Some began to wonder whether this was inevitable. After all, 3I Atlas was not a local body. It had formed around another star, in conditions humanity could only imagine. Its chemistry, structure, and history might reflect environments never replicated in the Sun's neighborhood. Why should it behave like the icy remnants of our own solar system? Perhaps the true error was assuming it would. The failure of models carried practical consequences. For the mission planners, it meant that the impactor had always been flying partly blind, guided by real-time navigation rather than reliable forecasts. For planetary defense experts, it highlighted how unprepared humanity would be if such an object posed a real threat. If we cannot predict how an alien body will move or react, how can we plan to deflect it? For theorists, it forced a reckoning with the limits of cometary physics. If our equations collapse in the face of interstellar matter, What else might we be missing? Yet the breakdown of predictions was also an opportunity. Each failure revealed where knowledge was incomplete. Each mismatch between model and observation pointed to new physics waiting to be understood. Plasma interactions on vast scales, volatile mixtures unknown in the solar system, structural heterogeneity shaped by alien suns, all of these demanded new approaches. For scientists willing to adapt, 3I Atlas was not just a puzzle but a teacher. As October 2025 wore on, the comet continued to evolve unpredictably. Night after night, observatories reported changes that defied expectation. In place of neat fits between data and theory, researchers were left with contradictions, gaps, and mysteries. For some, this was frustrating. For others, it was exhilarating. Science advances not when answers confirm what we already know, but when nature refuses to fit inside our models. And in that refusal, 3I Atlas had become the most extraordinary teacher of all. When the dust settled literally and figuratively, scientists faced a paradox. The mission had not gone as planned. Communications with the spacecraft had been lost earlier than expected. The impact had triggered a far greater outburst than models had forecast, and the solar wind around 3I Atlas had responded in ways that defied established physics. Yet in those very surprises lay the greatest value of the mission. What seemed like a setback quickly revealed itself as a breakthrough. The first silver lining came in the realm of chemistry. Spectrographs across the world recorded signatures of compounds rarely observed in our solar system. Methane, carbon dioxide, ammonia, and traces of complex hydrocarbons all surged in the hours following the impact. Some of these molecules are stable only at extremely low temperatures, suggesting that 3I Atlas carried ices formed in a star-forming cloud far colder than anything in our local neighborhood. For chemists, this was a once-in-a-lifetime dataset, a direct sample of material forged under alien conditions. Equally important was the discovery of variability. Instead of releasing gases in steady proportions, the comet emitted them in chaotic pulses. This indicated a nucleus with a layered structure, pockets of different ices stacked like geological strata. Such heterogeneity had been hinted at in solar system comets, but 3I Atlas displayed it on a scale never seen before. The implication was profound. Interstellar comets are not uniform relics but complex archives of their birthplaces. Each layer may preserve a different chapter of a star system's history. The second silver lining lay in plasma physics. By releasing so much material at once, the impact turned 3I Atlas into a natural laboratory. For a brief period, it functioned like a plasma generator, flooding the solar wind with ionized gas and forcing researchers to watch how the heliosphere responded. Satellites recorded ripples in the interplanetary magnetic field, disturbances that revealed how cometary outgassing can couple to the solar wind on massive scales. This was not just a curiosity. It offered new insights into how charged particles move through space knowledge, with direct applications for protecting spacecraft, satellites, and even astronauts from space weather. A third unexpected benefit came from trajectory analysis. Before the impact, 3I Atlas's motion had been difficult to predict. Its jets pushed and pulled it unpredictably, creating a blur of possible paths. After the flare, however, new outgassing jets acted like beacons. By tracking their geometry, astronomers refined models of non-gravitational acceleration. This improved not only the accuracy of 3I Atlas's orbit, but also the broader understanding of how comets behave under solar heating. What had been a modeling failure became a new calibration tool. Beyond the technical, the mission produced a cultural silver lining as well. For the public, the story was one of wonder. The comet brightened visibly. Amateur astronomers could photograph its changing coma, and news outlets carried daily updates. Instead of fading into obscurity, the mission captured global imagination. It reminded people everywhere that science is not about perfect predictions, but about venturing into the unknown and learning from the unexpected. For NASA and its partners, the data justified the risk. A small spacecraft had achieved something no telescope alone could have done. It had disturbed an interstellar body and revealed its secrets in real time. Even without complete telemetry, the ground-based and orbital observations provided volumes of information. The mission demonstrated that active engagement, not just passive watching, is the key to unlocking the mysteries of visitors from beyond our star. Perhaps the greatest silver lining was humility. The mission showed that the universe still has the power to surprise us, even in an era of supercomputers and precision models. 3I Atlas reminded scientists that assumptions must always be tested, that new physics often hides behind failed predictions, and that discovery is born not from control but from curiosity. In the end, what looked at first like a problem became a gift. The impact may not have followed the script, but it delivered a richer story than anyone had expected. The scientific silver lining was clear. In the strangeness of 3I Atlas, humanity had glimpsed not failure, but the frontier of knowledge itself. In the end, the strike on 3I Atlas was more than an experiment. It was a reminder of where we stand in the cosmos. A young species daring to touch something born around another star. The mission did not unfold exactly as planned. Signals were lost, models failed, and the comet responded with forces no one had predicted. Yet in those surprises lay the true gift. We learned that interstellar objects are not passive wanderers but active participants in the solar environment. We discovered chemistry never seen before, plasma interactions on scales beyond imagination, and a living record of alien history carried across the galaxy. The outcome was not failure but discovery, an expansion of knowledge that will guide future missions for decades to come. For now, 3I Atlas continues on its one-way path, glowing brighter as it nears the sun before it slips back into the darkness between the stars. Humanity will watch, record, and wonder, knowing we played a small part in shaping its story. And perhaps that is the greater lesson, that science is not about control but about curiosity. Each experiment is a question posed to the universe, and every answer reminds us that we are only beginning to understand the vast system we inhabit. If you followed this journey, take a moment to share your thoughts. Tell us where you are watching from and what time it is as you listen to these words. And if you want to stay with us as we continue to follow the mysteries of 3I Atlas and the cosmos beyond, don't forget to subscribe. The story of the stars has only just begun.